Today's topic is RAMs. RAM. RAM is a random access memory. RAM is short form for random access memory. It is also known as read-write memory. It is equivalent to a group of addressable registers. After supplying an address, we can read the stored contents of the memory location, or we can write new contents into the memory location. So we can read the content of memory location of RAMs, and we can also write new contents into the memory locations of RAMs. That's why it is known as read-write memory. We can read and we can also write. Core RAMs. Core RAMs were non-volatile. Non-volatile means they can continue to store data even when power is shut off. But these are expensive. Semiconductor RAM. There are two types of semiconductor RAMs. One is static and other is dynamic. The static RAM uses bipolar or MOS flip-flops. MOS is metal oxide semiconductor, FET. Data is retained indefinitely as long as power is applied to the flip-flops. On the other hand, a dynamic RAM uses MOSFETs and capacitors that store data. In either case, the RAMs are volatile. It means they can store the stored data will be lost when power is turned off. Volatile memory means the stored data will be lost when power is turned off. So the data is stored until the power is on. So semiconductor RAMs are of two types, static and dynamic. Static RAM uses bipolar or MOS flip-flops. Bipolar flip-flops means flip-flops using transistors, and MOS flip-flops means flip-flops using metal oxide semiconductor field effect transistors, MOS FET. And in a dynamic RAM, we use MOSFETs and capacitors. This figure A shows static RAM and this figure B shows dynamic RAM. In this figure A, which shows static RAM, here MOSFETs are used. And in this figure B, which shows dynamic RAM, a MOSFET and a capacitor is used. Static RAM. Figure A shows one of the flip-flops used in a static MOS RAM. Q1 and Q2 act like switches. Q3 and Q4 are active loads. We have 4 MOSFETs Q1, Q2, Q3, Q4 connected in this way. Q1 and Q2 act like switches and Q3 and Q4 are active loads. Q1 and Q2. These two MOSFETs are used like switches, and Q3 and Q4 MOSFETs are active loads. Active loads means they behave like resistors. Q3 and Q4, these two MOSFETs which behaves like active loads. It means these two MOSFETs Q3 and Q4 behaves like resistances, and Q1 and Q2, these two MOSFETs acts like switches. If one is on, then other is off, and vice versa. So at a time, one of the MOSFETs, either Q1 or Q2, is on and other is off. And in this way, a binary bit 0 or 1 is stored as X in this figure. Either Q1 conducts and Q2 is cut off or vice versa. A static RAM will contain thousands of flip-flops like this, one for each stored bit. As long as power is applied, the flip-flops remains latched and can store the bit indefinitely. Second is dynamic RAM. It is shown in this figure B. It uses a MOSFET and a capacitor. In static RAM, 4 MOSFETs are used to store a bit. Bit means 0 or 1, binary digit. So in static RAM, 4 MOSFETs are used to store a bit. 2 MOSFETs Q1 and Q2. These behave like switches. If one conducts, other is in cutoff condition, and vice versa. And Q3 and Q4, these two MOSFETs behaves like resistances. They behave like active loads. So here 4 MOSFETs are used, and in dynamic RAM only one MOSFET is used along with a capacitor. And we have 2 lines. One is called control line and other is called sense line, connected to MOSFET as shown in this figure. So we have a MOSFET and a storage capacitor connected in this way, and we have 2 lines, control line and sense line, connected to the 2 terminals of MOSFETs as shown in this figure. Figure B shows one of the memory element. It is called cell in a dynamic RAM consisting of a MOSFET and a capacitor. When the sense and control lines go high, The MOSFET conducts and charges the capacitor. When the sense and control lines go high, the MOSFET conducts and charges the capacitor. These are the two lines, control line and sense line, connected to the two terminals of MOSFET. If these two are high, then this MOSFET conduct and this capacitor will be charged. When the sense and control lines go low, the MOSFET opens and capacitor retains its charge. In this way, it can store 1 bit. When control line and sense line go high, means both lines are 1, then this MOSFET conducts and capacitor charge. And when these two lines go low, becomes 0, control line and sense line both become 0, then this capacitor remains charged and it store a bit. When the sense and control lines go low, the MOSFET opens and the capacitor retains its charge. In this way, it can store 1 bit. A dynamic RAM may contain thousands of memory cells like that of figure B. Since a dynamic cell consists only a single MOSFET and a capacitor, it has more memory locations than a static RAM of the same physical size. The disadvantage of a dynamic RAM is that the stored data must be refreshed every few milliseconds as capacitor charge leaks off. So it is much simpler to work with static RAM rather than a dynamic RAM. Now we see 3-state RAMs. Many of the commercially available RAMs have 3-state outputs. So we can connect or disconnect the output lines of a RAM from a data bus. Figure C shows a static RAM. This figure shows 3-state RAM with typical input signals. These are the input signals: WE bar, address, CE bar, and also have D in, which is input data, and D out, it is output data. The address bit select the memory location. WE bar and CE bar are control signals, write enable and chip enable signals. WE bar is write enable signal and CE bar is chip enable signal. And these two, WE bar and CE bar, are low active because of this bubble shown in this figure. Because this bubble is shown in this figure, these are low active, so we use bar with them. WE bar CE bar because these are low active. So these are active when WE bar is 0 and CE bar is 0. WE bar is write enable and CE bar is for chip enable. And we have this address line which select a given memory location. We can select a write, read or do nothing operation by using these control signals. Table of figure D summarizes the operation of this 3-state RAM. When WE bar and CE bar are low, it perform write operation. This means that the input data DIN is stored in the addressed memory location. The 3-state output data lines are floating during this operation. So for write operation, we must use CE bar and WE bar, both are 0. And these both are low active. It means that CE bar is active and WE bar is active when both CE bar and WE bar are 0 as shown in this table, and it will do the write operation. So if we want to write some content in a memory location, then we must keep CE bar and WE bar both low, and both are low active, and this will do the write operation and a content is written in a particular memory location, and output is floating in this case. So when CE bar is 0, WE bar is 0, this will perform the write operation, and this input data DIN is stored in RAM in a particular memory location. That particular memory location have certain address. This means that the input data DIN is stored in the addressed memory location. The 3-state output data lines are floating during this operation. Now when WE bar is high and CE bar is low, we get a read operation. So for read operation, we must keep this CE bar active. That means CE bar is low. So this will perform the read operation, and in this case we keep this WE bar inactive. It is high. WE bar is high, it is 1, so it is inactive, and CE bar is low, so it is active, and this will perform a read operation. So to perform a read operation, we must have WE bar 1, which is inactive, and CE bar low, that is active. We get a read operation. The contents of the addressed memory location appear on the data output lines. In this case, the content of a addressed memory location is shown in this output line D out. This is shown in this table also. When CE bar is 0, WE bar is 1, it will perform the read operation and output is now connected. It is not floating. Output is connected. It means we can see this D out, output data. So this is the read operation. We can read the data of a addressed memory location here in D out in output line. And the third case is when CE bar is 1. When CE bar is inactive, then whatever may be the WE bar, it may be 0 or it may be 1, the operation is hold. It means it will do nothing and output is floating. So for write operation, we must active both CE bar and WE bar. These are low active, so we must keep them low, that is 0 0. And for read operation, we must keep this CE bar active and WE bar inactive. And in this case, the data of a addressed memory location is shown in output line D output. When CE bar is inactive, it is 1, then it will do nothing. WE bar may be 0 or 1. Operation is hold, it means it will do nothing. When WE bar is high and CE bar is low, we get a read operation. The contents of the addressed memory location appear on the data output lines. When CE bar is high, nothing happens. Internal data at all memory locations is unchanged. Hexadecimal addresses. During a computer run, the CPU is central processing unit of a computer. During a computer run, the CPU sends binary addresses to the memory where read or write operation occur. These address words may contain 16 or more bits. We can chunk those zeros and ones into neat strings of hexadecimal numbers. Typical microcomputers have an address bus with 16 address lines having this format: address equal to XXXX. These are 16 bits, 4444. We can chunk this into its equivalent hexadecimal form. For example, instead of writing, if we have address of like this 0101 1110 0111 1100, these are 16 bits, 4 bits 4 times. We can write this address as 5E7C. 5 is for these 4 bits 0101, E for next 4 bits 1110, 7 for next 4 bits 0111, and C for next 4 bits 1100. And we write H in front of this. H is for hexadecimal address. So if we have address like this 16 binary bits, we can write this into short form 5E7C H. H is for hexadecimal address. So it is address in hexadecimal number system. The 16 address lines can access 2 to the power 16 memory locations. It is equivalent to 65,536 words. 65,536 words. It is 2 to the power 16. And we write it as 64K. 64 kilo. The hexadecimal addresses are from 0000H to FFFFH. Figure A illustrates how to visualize such a memory. 1 byte is stored in each memory location. These are the different memory locations having different hexadecimal addresses starting from 0000H to FFFFH. Each memory location contains a binary word of 8 bits. It is known as byte. So different memory locations have different addresses and have different contents in them. A particular address will contain a particular content.